All right, let's go and get started. Give me a moment. Let me get myself organized. So, if some of you were curious, whatnot, so that was my last visitor, so I can go back to being a jerk like usual, right?
I'll be on top
Oh, oh, thanks. Look it out for me. All right. Let me get my sign-in sheet and whatnot passed around. So, a couple things. Number one, you all have a present for me, right? Well, I have a present for you. All right. So, you can't put a value on a good education. You just can't put a... Like, it's called tuition, son. Look it up sometime. All right. I really do want you all to pay attention to this because this is kind of important in terms of the homework. I mean, I guarantee what's going to happen is this. I'm going to describe this. I'm going to go through it. And then somebody's going to say, going to ask a question in a week. So what's the D over B ratio we're supposed to use? It's like, well, I explained it. So, all right, let me start off by passing them out. You are a funny guy. 1, 2, 3, 4, 5, 6. Which, by the way, I'm Greg Michelson. I teach structural engineering courses. He did. And he got the...
I was awake and I felt like that was my
It's okay. It's okay. Here you go. All right, does everybody have one? All right. Y'all really need to pay attention to this, so bear with me, all right? All right. Okay, number one. Okay, read this out. All right, so on this problem, you need to do problem 412, but I'm doing a couple things to clear it up. So the live loads that are indicated in the problem are already reduced, so you don't need to do live load reduction. For your design, assume a D over B ratio of 1.5 inches, and then when you calculate H, just say it's D plus 3, okay? Which is what we've been using, or what we used in our previous example, so that should follow along. Make sure you compute the efficiency of your design, and you check tensile strain limits and minimum reinforcement limits. Okay, here's I think the one that really needs some clarification. So problem 2, right here. Use a beam width of B equals 20 inches, a height of H equals 45, and a D of 42 inches. So I'm telling you what the size of the beam is. Just pick the steel, okay? So there's a statement in the book regarding rho equals 1/2 rho max. Ignore that, okay? So on this problem, the difference is problem 1 is an unknown cross-section, and problem 2 is a known cross-section. So I wanted you to do both designs, okay? Problem 3, which I have listed as problem 2, so whoops. But that is a slab design, and live loads are already reduced. So it's number 2. No, but it's only number 1 in here. So that, well, again, I'm the one keeping the score. So. All right, this one, by and large, is probably the most important point I want to make regarding this homework assignment, and I'm just going to tell you. My design procedure that I've shown you all is different than what the book does, okay? So be ready for that, okay? When the book references these tables in the back and wants you to look up some value for mu over phi bd squared, and you're like, well, Dr. Michelson never even talked about that. What the heck's going on here? The method that I use is different than the one that's in the book. The reason the method that I formulated is different is because it's special. Goodness. No.
made with love.
I just answered that. I said it was my second mistake for the semester, but only my first mistake in here. No, I verified, and it's on the recording, so. Listen. The reason why my method is a little different than the method in the book is because my method doesn't rely on the volumes of tables that are in the appendix in the book. It requires a few more grunt calculations, but you don't need to go through 20 pages of tables, okay? So a lot of the calculations that we do in class, the book does by looking up values in tables. So when you're doing homework and it goes, oh, it went to appendix A-4 and found this value, and you go, we never even mentioned that in class, that's why, okay? So I want everybody to be aware of that right off the bat, okay? Does anybody have any questions? Yes?
So since you're telling us that the libraries are already reduced, is the book poor at conveying that to us?
No,
And
well,
every time we should know when they are.
I'll tell. Yeah, the book is poor at conveying that. It mentions it and then it just sort of moves on. If I was writing a book, I would show it at the very beginning, and then I'd probably indicate on every problem whether or not it's already been reduced or you need to go through and reduce it. No. Because then I'd have to write a book every 3 years because they update the code every so often. No, thank you. I'm on YouTube. My name's already out. I'm on YouTube, man. My name's already out. You just hit that subscribe button, by the way. Oh, I love this job. All right. All right. Homework 3 is due today if you haven't turned it in. Homework 4, it's assigned today. It's due Monday on the 20th. Monday, I'm giving you a solution, so no late homeworks on that day. I'm putting that off a little bit because you all have a weekend, or you folks in steel are going to be scrambling to get your steel design homework done this weekend, so I figure next weekend can be the concrete design homework. So see, I'm nice like that, aren't I? And I made it due after the celebration in steel, because the celebration in steel is on Friday.
In all reality, is there any way we got a DPQ exam Monday?
Huffman moved his exam to that Wednesday.
No.
Can we do it?
Hold on. Hold on. Hold on. Hold on.
Can we mail our homework in?
I draw the line at carrier pigeon, but all right. Oh, let's restore some order. Some order. Hold on. Well, order. I need a hammer. You said so. Professor Huffman has an exam on Wednesday, February 22nd. Do I understand that correctly?
Yes. 3:30.
All right. Hold on.
He just moved it though. Why don't you just go fight him for the day?
I don't know. I feel like it's okay because there's so much.
All right. Then we'll do this. Oh, I love this job. So hold on. Hey. Would Friday be beneficial? 24th. Would that be fine? Okay. I will do that. I will not add material to the exam by delaying it. Okay. We do one-way slab design and then we're done. That is exam 1. So. Now what?
How much more are we going to learn before we get to that?
This is it today. One-way slab design. This is it.
Yeah, so we have like a full
Yeah, can
2
we
Well-
weeks of learning.
up instead of back?
Yeah, but there's the problem with that. If we move it up, then I have to make your homework I have to accept it earlier. Okay. In other words, think about it like this. If I move it up a day, then I got to accept your concrete design homework on Friday, and you all have a celebration in steel on Friday. You see what I mean?
I think you guys should just take the L.
No. I'm happy to, no, listen, I'm happy to move it to ahead to the 24th, okay? All right. Here's what we're going to do, because we got stuff to talk about today. Here's what we're going to do. No. Here's the schedule. You all chew on it, think about it. Go ask Professor Huffman about it, whatever you want to do. We come back Monday, we make a decision, all right? Deal? Well, nobody, we got people saying nobody's on the same page or the same chapter. We're I mean, y'all are letting the pressure get to you in there. I'm just saying, you know. All right, hold on. I will entertain like another 2 minutes of discussion on this, and we're moving on. What's that? Do you all want to move? The way I look at it is this: we either move it to Friday or we keep it on Wednesday. Because if we move it to Monday, that is really going to be tough in steel design, because then your homework has to be turned in on the same day you have the big test in steel. So there's only so many options. So it's up to you. You tell me, Wednesday or Friday?
Friday.
All right, hold on. All right.
No change. You're reviewing on Wednesday anyway, so we'll remove the review to Wednesday, right?
Yeah.
Yeah, so, I mean, it's not like...
Well, we're going to have an exam review before the exam. I don't do that in all my classes, so.
It'll be fine on Friday. Let's do Friday.
It's what we're going to do right now. We are going to take a vote, and I need, now, I might have said Wednesday just now, and then everybody would have found you over here would have found you in the parking lot or something. So, all right. Here we go. Everybody pay attention. Who votes to have the exam stay on Wednesday? Oh, goodness. I need hands up, like up in the air, 1, 2, 3, 4. That, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
He can't hold his arm. He's broken.
12 and change. All right, so how many votes to move it to Friday? Oh, God. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Oh, shit. Does it change? Now we need an executive order.
Jesus. All right, here's what we're going to do. We're going to come, we're going to come back to this on Monday. Chew on it, think about it. I might talk to Professor Huffman. We'll see what happens. Slab design. Let's talk about slab design. Goodness gracious. God. What if I had a visitor on today? God. Oh, that's what it is. All right, it's slab design. Come on, let's get back to concrete. All right. So, what the heck was I talking about? All right. All right, so we talked about this like at the very end last time. We were sort of closing up and didn't really get into some detail. But I want to be clear that in reinforced concrete design, there is more going on than just the beams. We have the slab to consider. So it's a very simple design, but it's something we need to do. So the trick, or I guess the caveat I should say for it being a simple design, is if you're only considering one-way bending action. So a one-way slab is designed to only bend one way. All right? The reinforcement and the structure that it is located in is oriented such that the slab bends as you'd see above. It's either going to bend like this or it's going to bend like that. That's one-way slab design. Two-way slab design is if the slab in a roundabout way, it almost kind of looks like a graduated example of like what a balloon would look like, how it sort of bends in two directions. We use that a lot in instances where we really like to shallow up the depth of the floor system. I mentioned an example last time of Washington, D.C., of how they use a lot of two-way flat slab construction in D.C. because you can save a couple inches on a floor system. That might not seem like a lot, but take that and add it up over 30 or 40 stories, and it's funny how you get an extra floor in the building. And an extra floor in the building means extra rent for the development of the building because they got more floor space to rent out to lobbyists and law firms and the like. So, excuse me. So flat slab construction can matter. Now, let me say this. It's tough. And more often than not, the most common slab design technique is to use one-way slabs. It's just simpler. So you got a beam, you got another beam, slab in between. Just design it as a one-way slab, and it's incredibly simple. Now, when we did beam design, we looked at two different design problems. We looked at design of a beam with an unknown cross-section, and then the design of a beam with a known cross-section. In other words, we know what the beam looks like. We know its sizing. Slab design falls into that category, and here's why. A slab is really just a really wide beam. That's all it is, It's just a really wide beam. So what we do is we say, all right, let's take a slab and let's just take a strip of that slab, and we'll keep it simple. We'll take a foot-long strip, 12 inches. So we'll say our beam width is 12 inches. There's the width of the beam. Well, if we've got the width of the beam, and we say, all right, we can compute the depth or the thickness of that slab just using API minimums, then there you go. That's it. For slabs, the cover requirement is not 1.5 inches, it's 3/4, because you've got more reinforcement spread out over a larger area, so you don't need as much cover. In the end, it's pretty straightforward. The only thing that I guess is a little more unique to slabs than it is to beams is because slabs are by their very nature inherently thin elements, under temperature variations and various conditions, what happens when you heat up an element, it expands, and you cool it down, it contracts. Slender and thin elements like slabs can be subjected to cracking under those conditions, more than a beam would. A beam is a really stocky, heavy element. It's not going to experience that type of cracking, or it's not going to be subject to as much of that type of cracking as a slab would. So we add temperature steel, if you would, to a slab as well. Yes, sir?
Yeah, so the beams, we place the reinforcement along the width of the beam.
I mean, you're talking about the stirrups?
The reinforcement,
Well, we place it longitudinally along the bottom. Are you talking about the main steel, or?
yeah, longitudinally.
Okay.
But here it's kind of different.
No, okay. What I'm saying is the main steel still goes that way. In other words, when we're designing reinforcement, the slab is bending like this. So the main steel, like the main reinforcement, would sort of be like this. Like maybe, let me see if I can get the pen to work with me. It's not like me. Hold on. That's big. That'll be all right. So the main steel is going like this, okay? The main steel is going that way. But I'm saying that for slabs, because they're inherently slender elements, we also need a fair amount of steel going this way, just to resist cracks that could happen due to things like shrinkage or temperature variations or things like that. So the red lines, the lines going this way, they're the ones that we're going to be sizing for strength. The blue ones, the ones going transversely, those are simple, but we still need to put them there. Did that answer your question? Everybody else okay with this? Yes, sir. okay, so to clear that up, so we're going to be like deriving and solving for how much steel we need for strength. As for the blue steel, the code says just put 0.018 BH, just put that much steel. So we just calculate it and bam, it's not an involved calculation. It's just something you have to do at the very end. Does that make sense? You'll see the method here in a little bit, and I think you'll go, oh, okay, this is what he was talking about. All right. Now, like I said, the beam width is just kept at 12 inches. The beam depth comes from this right here. And we've already seen this before because we used this to determine the minimum beam size for the estimates. This is essentially a thickness requirement for deflection considerations. So if we've got a solid one-way slab and it's simply supported, the thickness must be at least L over 20. So we'll just use that, and that'll be our thickness. And that's it. That's all there is to it. So here's our design procedure, and it's very similar to known cross-section design. We compute factored moments. We know the cross-section because the width is 12 inches and the height is the minimum height. That's it. We assume phi is 0.9, compute the required nominal moment. We calculate a rho for design purposes. Again, we know what the beam looks like, or in this case, the slab. We know what the slab looks like, so we do not use 0.18 FC prime over Fy because that is when we're just shooting in the dark. We have no idea, so we just start a value and say, hey, let's just go with it. When you know what it looks like, you can derive. So this is that derived formula. Calculate rho required. Take that to calculate rho BD, your required area of steel, pick some steel, and there you go. That's it. Okay? Now, you have to choose both main steel and temperature steel, so we'll look at that. Main steel, or the red bars, if you will, in that previous instance, are the rho BD. Temperature steel, pretty simple, 0.0018 BH. H, though, that wasn't a typo. That is correct. So it is 0.0018 BH. All right? It's literally plug and chug. We can take it and look it up. It's pretty simple. Now, a few rules that need to be mentioned. So main reinforcement, the bar spacing must be the minimum of 3H or 18 inches. So you'll see where that comes into play in a second. 5H and 18 inches is for temperature steel. But what I'm getting at essentially is this. I gave you all, I believe, a slab design aid, didn't I? Looks something about like this. Did I give you all this, and all it has is this one table on it? Yeah. Okay, all right. So everybody open that up real quick. Okay. While you all are doing that, I will do this. Okay. So what we're going to do is this. We're going to look up various different possibilities of reinforcement patterns. So you'll notice, let me explain sort of how this table is computed. So the idea is this. We have bar numbers spaced at given increments. So, for instance, if you have a number 9 bar, what's the area of a number 9 bar? 1 square inch. So if I have number 9 bars spaced at 12 inches, see this, number 9, 12 inches, that is 1 square inch per foot. Make sense? What if I had number 9 bars at 6 inches? That would be 2 square inches per foot, right? Make sense? When we do slab design, we're just assuming each beam or each portion of that slab is 1 foot wide. So we're just figuring out how much steel needs to go in that foot, and we'll just space it evenly. The one thing we have to make sure of is that we're not selecting a reinforcement pattern that violates bar spacing. So that's what that last slide was about, that main steel has to be either a 3H or 18, like that's the maximum bar spacing. And for temperature steel, it's 5H or 18. So pretty straightforward. Sound good? Any questions? All right. I think you'll find that slab design is pretty simple. It's not too complicated. The only other thing I guess that's worth mentioning is that when you do slab design and you calculate your moments and things like that, you're going to find that your moments are really small. Okay. For instance, when we do beams, we were looking at what? 300-foot kip, 400-foot kip, something like that. You might get, for a slab element, you might get 5-foot kip or 6-foot kip, because you're talking about an element that's only yay wide and about yay thick, okay? And its tributary area is just that 12 inches. So that little element is just not responsible for a lot, okay? So don't freak out when you do slab design and your moments come out real small. They should come out real small. All right, sound good? All right. Bless you. Expansion of your reinforcement. What do you mean by expansion of your reinforcement?
When it heats up,
That-
it expands. Like, because a shallow slab has a high possibility of cracking.
Well, that's a good question.
Like, maybe not. Maybe it doesn't happen. But this will heat better because it's shallower.
Here's a simpler way to answer it. So you go back to deformable, and if you remember, there's a constant called alpha. It's the coefficient of thermal expansion. And alpha is a material, an intrinsic property for a material. In other words, there's a different alpha for steel than there is for wood, for aluminum, for plastic, etc., right? One of the beauties of reinforced concrete is that steel and concrete have different alpha values, but they're not that far off. Okay, so steel and reinforced concrete, or steel and concrete, together, technically the steel and the concrete have different rates of thermal expansion, but they're not that different. Okay, I think we have bridge elements that are outside. Go from 100 degrees in the summertime to minus 15 in the winter, and they're fine. I mean, they're not going to be fine forever. But they work pretty well together. There's a push now in the world of concrete design to use different types of reinforcements. One of them is to use things like polymers, like FRP, reinforced polymers. One of the problems is that FRP and concrete have different rates of coefficients of thermal expansion, so that's an issue. So it's actually not as much an issue for steel. So that's a good question, though. That is a great question, right? And it's sort of a happy coincidence, like 11 times 10 to the minus, one's like 12 times 10 to the minus 6, so they're pretty close. Any other questions? This is good stuff. All right, so let's design a one-way slab, okay? So the span length is 10 feet, and I want to explain what that means when I say span length, because it might sound a little strange, but span length for a slab, actually, let me ask you that. So span length for a slab, what do you think that is in terms of girders? Like, how could you relate that? Exactly, it's the girder spacing, right? I mean, the span length for a slab, how far is the span? That's the distance between the girders. That's another reason that your moments are going to come out way low, because you're only going to have 10-foot spans. You're not going to have 30, 40-foot spans. Make sense? I'll try and draw a neat little pretty picture to make that make sense. Okay. So we got 4 KSI concrete, 60 KSI steel. We have live load is 200 pounds per square foot, which I could ask, well, is that reduced or not? But if you recall, you can't reduce live loads that are over 100 PSF anyways, This is like library loads where you wouldn't reduce them, right? Remember, a library is like 150 pounds per square foot. This is a load. This is a serious load. So no reducing that anyways. The only dead load is the slab self-weight. Sound good? All right, so let's check it out. I think you're going to find this is pretty straightforward. I'm going to delete that. All right. Okay. So let me sort of explain what was going on in terms of that girder spacing issue. So I'm going to do my best to, you don't make fun of my 3D art, but bear with me. Okay. All right. So what we've got going on is this. All right. So let's see. We've got that. We got something about like that. Okay, so we've got a floor slab sitting on two beams. Now, one of the things you might notice is I'm treating the floor slab as if it's just sitting on the beams. What I'm then going to do after slabs, this won't be an example, so don't worry, but we're going to look at T-beams, where the slab and the beam are cast together. So can you take a part of that slab and count an effective towards the beam? And the answer is yes, you can. All right. So when I say span length, I'm essentially saying that the slab is spanning 10 feet, but that's the girder spacing when we look at the beams. Does that make sense? So the strip that I'm designing is actually this strip right here, something about like this. That's my cross section. All right. Sound good? Okay. Now, let's see. So let me ask you this. How wide is this right here? How wide is that? There we go, 12 inches or a foot. So if I look at the beam cross section, what I have is a beam that looks like this. So the width is 12 inches, and this is the height, which I don't know yet. Okay? And I'm trying to figure out, what's that? What's up? No, what we're going to do is this. We're just going to design for one 12-inch strip, and whatever reinforcement pattern we got there, we'll just repeat that all over the place, and then that'll be our reinforcement. Okay? Does that make sense? Okay. All right, so we need height. We're also going to need D, okay? We're going to need the effective depth. Main reinforcement steel is going to... Main reinforcement steel is going to go like this. All right. The temperature steel is going to go like this. Oh, God. No, we're going through this. We are finishing this, all right? Okay. So is everybody okay with the fact that the main steel that we're designing is this way? Or in other words, it's going along the span length of the element. Okay? Is everybody all right with that? The temperature steel is going in and out of the screen. Okay? That's just there to prevent cracking, and that'll be pretty simple. All right? Now, before we get into this, okay, what we're going to do is this. we're going to make a pretty blanket assumption, and you can do this on your homework as well. We're going to use for cover, we're going to take the effective depth to be h minus 1 inch. And here's why. So if I look right here and I say, all right, I've got some rebar like there, there, and there, I am saying that we need at least 3/4 of an inch, okay? But the effective depth goes to the center, right? Like that would be the distance D. So I can't take h minus 3/4 of an inch because the center of the rebar would go down and I wouldn't be meeting that requirement. So just to keep it simple, I'm just going to say let's just go h minus 1 inch. So is everybody all right with that? Okay. All right, so I didn't want to just throw that out there. I wanted that to make sense. Okay, so watch with me up here. So the cover has got to be 3/4 of an inch for a slab. But I can't take D to be h minus 3/4 because D goes to the center of the rebar. So I'm taking the rebar and I'm lifting it up a tad to account for that. So I'll say D is, we'll say h minus an inch. And that's fine. If you want to raise it an inch and a quarter or something, that's fine too. Okay? That make sense? All right. Yeah, pretty much. Those are, yes, exactly. Those are very easy assumptions to go off of. Unless it's stated otherwise, like I would just go with that. Because again, a lot of this goes off of commonly available rebar chairs and things like that. So, sound good? All right. Step 1. So what's step 1 for our slab design? Oh, making you all go through your notes? We need moments. We need factored moments. So, compute MU. All right. So, we need self-weight and we need live load. So, remind me, how do I compute the self-weight of any flexural element? I take the unit weight of steel and do what with it? Times what? No, it's not the volume. Yeah, reinforced concrete, but I'm talking about how do we just compute self-weight in general? Take the unit weight times what? The area. There we go. Remember, gamma BH will give us the weight per foot. Is everybody okay with that? I mean, we've done that on a couple examples, but I want that to be clear. All right. Now, in order to do this, we need the height. So what we're going to do is we're going to take the height as the minimum that is allowed by ACI, which is the length over 20. So how long's the slab? 10 feet. There we go. Okay. So what does that come out to be? There we go. So that's how thick our slab is. So we're going to take B to be 12 inches, H to be 6 inches, and D to be 5 inches. All right? So if we've got that, then we can compute unit weight and we can compute our live load. So our unit weight, you said, was gamma times the area. So our self-weight, W sub naught, is gamma times the area. All right, anybody see anything wrong with that? There we go. So I'm going to do 1 square foot. Yes, for the slab, for the slab.
What other dimension did you give us?
It wouldn't matter for the slab, it would matter for the beam. That's the span length for the beam.
Right, but
Yes.
I'm just curious if he gave us the other dimension, which one would use for the slab length that was long. Like
If the beams went this way,
no, the slab. So
if I gave you that dimension,
yeah, so
you'd throw it away. No, seriously, you wouldn't use it. I mean, it wouldn't matter because, again, I don't care how long the beam is or the slab is this way because I'm just designing a 12-inch strip and I'm just going to repeat. Does that make sense? No, that's fine. What do we got here? Say it again. I got a second on that. Okay, now, let's think about this. The live load. What's the live load? Oh, no. This would be kips per foot. That's a good question because it's kips per cubic foot, but I took these square inches and converted them to square feet. So everything's in feet now. It's a good question. Now, okay, what was I saying? Oh, live load. What's the live load? 200 what? Pounds per square foot. So what do? I take a PSF and I multiply it by a flexural element's what to get the distributed load? Somebody said tributary area. We need the tributary area, right? Now what I'm going to do for a slab element is this, is I'm just going to say the tributary area for that strip of slab is 12 inches. It is responsible for 12 inches of floor because it is the floor, right? So it's going to be responsible for it. I mean, that's what we're designing. We're designing the floor. So this is how I'm going to handle this. I'm going to say that the live load is just that pressure times B, right? So it is, what's the load? 200 pounds per square foot or 0.2 kips per square foot, right? So over 12 inches, but that's a foot. So isn't that just that? Simple, right? Everybody okay with that?
So is that live load like just assuming like the heaviest load possible?
We're designing a floor system that needs to hold up like an ice skating rink or something. Because, yeah, no, like there are loads like that, and they're like 200-300 pounds per square foot. So yeah, this floor that we're designing right now is holding up a lot. Like you could say it's holding up heavy machinery or a library or something like that. So yeah, this would not be a typical floor in an office building. We'd use something like 40 or 80 or something like that.
Now, I think I mentioned this in a previous class, but I know a structure in Cincinnati that they were going to have a pool on a floor on
Oh,
the
yeah.
level, and the designer designed it for the subway of the pool without the water.
Smooth.
They built the whole thing and then realized
There's water in it.
there's water in it, and it's got the whole problem.
Ooh. That's like fundamentals. All right. What do we need to do to this load? We got a dead load and a live load.
You gotta do the thing.
Do the thing with the stuff. So 1.2 times 0.075. I didn't reduce it. No, this is factor. If anything, this is increasing it. Reducing, I'm talking about live load reduction, the like 0.25 plus 15 over square root of KLLAT. I'm talking about live load reduction. Well, it was like 3 or 4 weeks ago. All right, what do we got for this? Say it again. All right. So what do we do with that?
Plug it into the MU equation.
There we go, which is?
I don't know.
Thank you, Mr. Wickley. Thank you. All right.
Oh, I definitely do that.
Does everybody have this? All right, all right, all right. It's one of them days, isn't it? What's that? I thought we were too. All right. So help me out. Help me out. I know we're running out of time, but we're going to chug through as much as we can. What's our length? Yes, you do. What room are we in? Like, oh.
So what's 41 divided by 8? That's like 7 and some change.
Oh my goodness gracious. I heard somebody say it. Oh God. Woo! All right. Everybody okay with this?
No. Why is it not 7?
All right. Thank you for looking out for me. I do appreciate that. All right. Let me ask you this. Look at our moment. Our moment is like 5.125 foot kips. That's small, right? I mean, we were getting like 400 foot kips, 300 foot kips on previous problems. That's okay. We're talking about a slab, so that is perfectly fine. Okay, so here's what we're going to do because, yeah. I don't even know what's going on anymore. All right, so we're going to finish this problem on Monday. Okay, hold on. We are going to finish this problem on Monday, all right? We're going to finish it on Monday. And in all seriousness, guys, in all seriousness, but before you all like just sort of completely check out, I really do want you to think about the exam because we were split right down the middle in terms of Wednesday or Friday. I'm sure that the rec center has, octagon facilities if you need to work out your arrangement. All right. Okay. It's a good point. Look, you all chew on it. Come back to us on Monday with a clear. And if not, I'm just going to make a decision. So, yes, sir.
I have work at 3 in the morning on Wednesday, so that's another reason why I want off Friday. Yeah, so Kyle is. We all have work at 3 in the morning.
That was a large quantifiable amount of something, I will say. So, I won't say it because I'm recording. Which I might need to unlist this video. I'm just saying. All right. Y'all have a good weekend.